This is a supplemental video for lesson 2.2 on simplifying radicals. We're taking an extra day with this because a lot of us struggled with it, being a new concept. Even though we looked at the rules yesterday, a lot of them, because there was so much, it was a lot to absorb, and some of us are still struggling with it. So we're going to go over a couple examples, especially the ones that are like your elephant riddle. So the first three examples are going to be like the problems on the elephant riddle. And the last two will be like some of the division problems from your worksheet. So just before we begin, we're going to review. I'm going to be using perfect squares to reduce. So I'm going to try to divide out the largest perfect square. If I don't get the largest perfect square, then I'll have to keep breaking down whatever I have on the other side. So we'll go through an example of that. The product rule does say that we can take something and split it into the multiplication of two factors that multiply to it. It also says that I can take two things that are under a radical and multiply them together under the radical. So looking at example 1, this could have started out as a problem like example 2 where they were all under the radical, but I actually want them separated so I can think about each individual piece. And this is supposed to be an x to the 9th. So square root of 28 times square root of x to the 9th. So I have square root of 28, the largest perfect square that goes into 28 is 4. So I have square root of 4 times 7. That's what the square root of 28 splits into. The square root of 4 is 2, and square root of 7, I double checked my list of perfect squares to make sure I did get the highest one. Nothing on that list will go into 7 except for 1, so I leave that as the square root of 7. So square root of 28 is really 2 times the square root of 7. I'm going to put a multiplication sign for there for right now. Normally we don't do that on our in our answer, but I'm just doing it for right now so that we can see that. Now our x to the 9th, we did do this one using rational exponents. Whenever we had variables, we chose to do it this way because there's a quick trick to doing it. If you don't like that, you could say, oh, it's the square root, so I'm going to look at how many factors of x squared I could get. So if you need to, you can see me to get help with it that way. But my preference is for you to look at this as x to the 9th. And since we're taking the square root, we're raising this to the 1/2 power. And some people say, well, wait, why are we doing that? Well, think about this for a second. We reviewed it the other day. 3 squared is 9. Then if I took 9 and raise it to the 1/2 power, it's the same as raising 3 squared to the 1/2 power, becomes an exponent of 3 to the 1st. Square root and squaring are inverse operations, and so is squaring and raising it to the power of 1/2. So raising it to the 1/2 power is the same as taking the square root. So this is x to the 9/2, and 2 goes into 9 4 times with a remainder of 1. What this means, or the trick that we looked at the other day, was that this meant that 4 factors of x will come out of the radical. 1 factor of x will remain under the radical. Now using my rules of exponent, or the rules of radicals, the product property, I can put these two together under one radical because square root of 7 times square root of x is the square root of 7x. And the 2 and the x to the 4th are outside of the radical, so that becomes 2x to the 4th. And that is my final answer for that problem. Example 2. I'm going to do exactly what was already done for me in the first example and split these up depending on their base. So I have the square root of 40 times the square root of x to the 7th times the square root of y squared. The square root of 40 will split down square root of 4 times square root of 10. No other perfect square goes into 10, so I know that that will be completely simplified. This is 2 square roots of 10. The x to the 7th I will rewrite as a fractional exponent. X to the 7th raised to the 1/2 power is x to the 7/2. 2 goes into 7 3 times with a remainder of 1. So there will be 3 factors of x that come out of the radical and 1 factor of x that remains under the radical. Square root of y squared is really going to be y to the 2nd the square root is like raising it to the 1/2 power. So y to the 2 over 2, that goes in evenly as just 1 without a remainder. So one factor of y escapes the radical, and there are no remaining factors under the radical. The numbers that are under the radical get put together under the radical. Square root of 10 times square root of x is the square root of 10x, because 10 times x is 10x. The numbers outside of the radical come together. That'll be 2 times x cubed times y. I don't need to put the times sign. It's implied if there's no addition or subtraction signs between them. Example 3 is just like example 2. Feel free to pause the video and try it yourself if you'd like to first. The square root of 48, the largest perfect square that goes into the square root of 48, is 16. It's 16 times 3. The square root of 16 is 4, so it's 4 square roots of 3 for that, because I can't break down the square root of 3. The square root of x to the 11th and square root of y to the 8th and square root of y, or z squared, I'm going to change to exponential form. This is x to the 11 halves, y to the 8 halves, z to the 2 halves. Two of these work out really nicely. This one, however, 2 will not go into 11. It goes into 11 5 times with a remainder of 1. It does not go in evenly. Therefore, 5 factors of x escape the radical. 1 factor of x is still stuck under the radical. For my y, 8 divided by 2 is 4. So y to the 4th, because it's 4 with a remainder of 0. No factors are left under the radical. For my z, 2 over 2 is 1. So it's just z, because it's z to the 1st. In my final answer, I will group all the ones that are under a radical together. So 3 times x under the radical is the square root of 3x. And then I have 4x to the 5th, y to the 4th, z in front of the radical. All of those terms still being multiplied together. Before we go over the division x examples, and there's really 2 types of problems that we've dealt with so far. There will be a third type where we get stuck with a radical in our denominator and we have to do something special to take care of it. But for now, for all of the problems that were on the day 1 worksheet of 2.2, they followed one of these 2 types. When we're doing the quotient of roots, we normally start with a fraction. We might start with 2 radicals, though, 2 radicals that are divided. And so I can bring them together under 1 radical. Now there's a time where I want to separate them and a time where I want them to stay together, at least initially. Eventually, I do want to separate them. The time where I want to leave them together initially is when the denominator is a perfect square. If the denominator is a perfect square, separate them immediately and take its square root. Now you don't have to worry about any square roots in the denominator. You can just leave that denominator of 2 there until the very end, and then, if possible, simplify the fraction. The numerator that we had in our example was able to be reduced, so we broke down the square root of 18 and put that in the numerator. So whenever you have a perfect square in the denominator, separate it so it's square root of the numerator over square root of the denominator, and simplify the denominator immediately. If in the case they are not, if the denominator is not a perfect square, then you either want to put them together under a fraction, or maybe it already started out as a fraction under the radical. Your goal then is to reduce the fraction. In this case, it reduced that there was just a denominator of 1, so that was helpful. But even so, you want to reduce it because it may reduce to perfect squares. At least that's what the ones that we've done so far will do. It won't always work out that way, and we'll add that trick in our next lesson. So when I look at this, I see 32, and it is not a perfect square. No number squared will give me 32. That's not a whole number anyhow. So I need to see if I can reduce the number that's under the radical. 54 over 32, both are divisible by 2, giving me 27 over 16. So now, instead of the square root of 54 over 32, I have the square root of 27 over 16. Some of you are like, well, wait, where did those 2's go? Well, that's really, dividing by 2 on top and dividing by 2 on bottom. I'm just reducing the fraction. 2 over 2 is 1, so it's okay that I did this. This is really times 2 over 2, and that's a factor of 1, so I don't have to worry about that. Now that I see that there's a perfect square down here, I need to separate them. Square root of 16 in the bottom, square root of 27 on top. The square root of 16 becomes 4, because 4 squared is 16. The square root of 27 is not a perfect square, unfortunately, so we do need to break it down. Its factors are 9 and 3. And the square root of 9 is 3, so this will give me a numerator of 3 square roots of 3. The fraction 3/4 can't be reduced, so this is my final answer. So yes, once I saw a perfect square down there, I separated the numerator and denominator so I could take the square root of that denominator. But before that, it wasn't a perfect square. I needed to try to reduce this fraction. That is different. How I start this problem is different from how I start this problem. And the problem to the right, the square root of 20 over 9, is the square root of the fraction 20 over 9. The denominator is a perfect square to begin with. So I immediately want to separate this using the quotient property, square root of 20 over the square root of 9. Because now I know the answer to the square root of 9 is 3. The answer to the square root of 20, a little trickier. I do need to break it down. It's the square root of 4 times the square root of 5. 2, so this is 2 square roots of 5. Now I would still check my fraction in the end to see the numbers outside, 2/3. Could I reduce 2/3? I cannot. And I couldn't reduce the 5 anymore because no perfect square goes into it. So that stays square root of 5. So my answer is 2 square roots of 5 over 3. These are like some of the division problems on your worksheet. There weren't many, but there were a few. So go back and look at those. If you didn't get them right the first time, see if they make more sense now. The problems at the top of the page, at least example 2 and 3, are they're similar to the problems that you're going to see on the elephant riddle. The difference is, on your elephant riddle, they take care of something that we're not addressing. We're assuming that our answers for x and y are positive, and we're not solving, so I'm not worried about it. But if we were solving, we might be a little more concerned. But what we have here is, on the answer key, they're going to tell you, well, wait a second, y was squared under there. So y could have technically have been a negative number. So when you take the square root and you just tell me it's y, I don't know whether y is positive or negative. So on your answer key for the elephant riddle, you're going to see absolute value signs around those ones that were even degrees under the radical. Don't worry about it. For what I'm asking you to do, I want you to ignore the absolute value symbols for now. We're assuming in what we're doing that our answers for those variables are positive as we do this. We will get to some cases where they're not, but that's far down the road from here. So then we'll deal with that when we come to that place. So right now, your answer for this, possibly if this were on your sheet, would look like 2 and then the absolute value of x cubed y, and then square roots of 10x. So this, which was the answer we would get, will look like this on your answer key. This is not a problem from the elephant riddle. I'm just telling you that when you're checking to see if you have the answer on the answer key, ignore the absolute value symbols. Hopefully this helps clarify for some of you who might still be struggling. On Monday, we'll go over questions from the elephant riddle, and we will be adding the concepts of adding and subtracting, rational expressions, or not rational, radical expressions, and rationalizing the denominator.